Good evening, sir.
Good evening, ma'am.
Sir, am I audible to you?
Yes, yes, audible, ma'am. I'm audible?
Yes, sir.
Yes, thank
Sir,
you.
so now next talk is from Dr. S. Venu Kumar, who is working as a lab manager in NMDC Steel Limited since 2023. He has done his PhD in the Department of Metallurgy from NIT Tirchi and followed by the master degree from the same university, same institute, and as well as same department in 2004-8. Prior to this, he has 9 year working. He has worked 9 years as an assistant professor in the Department of Mechanical Engineering in JNTUH Hyderabad. He preferred to teach metallurgy and material science, heat transfer, additive manufacturing, strength of material, production technology, metrology, machine tool, theory of a machine, and fracture mechanics. He has published more than 45 papers in journals as well as published more than 20 papers in the national journals. More than 30 papers presented in the national and international conference. He has one patent which is granted, and he is convener of three international conference. He has guided more than 10 PG students and 40 UG students. Sir, please welcome to this FDP and please deliver your talk.
So, thank you, ma'am. Thank you for a nice introduction. So, first I'll share my presentation.
Hello? Yes,
Uh,
sir.
yes. Okay. Can you see my presentation right now? Yes, ma'am. Can you see my presentation
Yes, sir,
right
sir.
now?
It's visible, sir. It is visible, sir.
Yes, yes, yes. Thank you, thank you. So, yes, I'm changing the slides. It's changing, right?
Yes, yes.
Yes. Okay. Okay. Thank you. So, thank you, ma'am, for giving this opportunity. So today I'm going to explaining about smart manufacturing and industry 5.0 application, especially the smart manufacturing. Nowadays, everyone talking about the 3D printing or additive manufacturing. So today my topic is on application of 3D printing in industry 5.0. So before going to that, just let me give small introduction as I am Dr. S. Venukumar, working as lab manager in an MDC steel plant. So today I'm going to talk about the mostly on Industry 5.0 and smart manufacturing. That among the most additive manufacturing I'll cover, and application of different 3D printing. What are the different classification of 3D printing? And I'm also discuss about the application and how it is starting to the now how we are using. So I'll discuss about the even application of 3D printing. So before going to this industry 5.0, how it is started, so we should know about this. All other industry 1.0, 2.0, and so we'll see 3.0, 4.0. Industry 1.0 is that it started. It's started in around at the end of 18th century. It's like in around 1784. So their engine started with the steam. Then after later 100 years later, then in this industry 2.0, in this era we are seeing the mostly the mass production. So engines used to run by electricity and assembly lines we are seeing in this era. After 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 100 years, again we are seeing industry 3.0. In this 3.0, so mostly we started the using by using of computers, electronic devices, and started of automation just started in this 3.0. So in industry 4.0 now mostly it is around digitalization. So we are seeing internet connection, device data connection, data analysis, right? And so, what are the technologies? Mostly there are many technologies. Mostly we are talking about the AI and ML, artificial intelligence. So, what is artificial intelligence? It's mimic our human body. How human is thinking, how human is listening, how human is behaving. It simply mimic the uh, human approach. Thus, AI and machine learning, deep learning, all these we are using by using different mathematical formula to uh, convert physical simulation. And we are also seeing in this era, Industry 4.0, big data, and there is a lot of data, and so we should store that. And Internet of Things. So IoT is all of you know that it's in industry there are different devices, different systems, right? So it will connect all the device. For example, it will connect machine to machine. Okay, one machine is stopped, so it will inform this. So my has some problem is there in this my machine, by using advanced technologies like AI, ML, deep learning. Because due to this advanced techniques, my machine now my production is stopped. No, so the machines will talk, and it will give the information to the another device or another factory, another. Okay, it's connecting between the system. It's a device to device. And we are also talking about this augmented reality, means you no need to present. So without you, even you are going the, we are you are present in the remote area also, you can see what's happening in your system, what's happening in your factory, or what's happening uh, in your manufacturing area. So you can see that, you can see by these technologies. And you can see the simulation and augmented reality. And we'll talk about this additive manufacturing, right? Yes. And limitations. What are the why we are talking? We are talking so many advanced technology in Industry 4.0, but still, why Industry 5.0 is coming to the picture? Actually, it's a Germany. Germany is started the Industry 4.0 to increase the GDP, to increase GDP in at the 21st century. So we have seen 2008, in around 2008 to 10 we have seen big ration, and GDP is lost. So to increase that, so they are increase the production, they are increase the GDP by using this advanced technology. But so due to that, this increase the production, that's good. But still there are so many limitations we are seen in the Industry 4.0. The first one is the obviously the cost is high, because due to this advanced technology, because we have to use this sensors, different high advanced equipments we have to use, so that high initial investment, the cost is very high. And the data management, because of the lot of data. So because of that, we are using high connected systems, high IoT system, high AML techniques. There is a lot of data. We have to store that. And ethical and social concerns. It is I want to more talk about this and cyber security risk, and environmental impact. It's mostly it is environmental. Nowadays we are everyone is talking about this carbon footprint, right? So more pollution, more carbon footprint. So it should be as minimum as possible. And because of the sudden using high advanced sudden technology, there is no standard. So everyone should follow some standard and regulation, so that it will does not affect the environment. It will There will be a cyber security. So there will be ethical and social concerns. If there is no standard and regulation, so all other limitations will come into this picture. And environmental impact, because you're increasing the productivity, that's good. But at the same time, if a small component, if you want to manufacture, there will be a lot of wastage of material. There is, so that where that material is going. And we are using this industry 4.0, we are using, all of them are using this, all electronic devices, right? We are using so different electronic devices. So all the weight after uses, where it is going, it will impact on the environment. And ethical and social concerns. And it's because of this high advanced technology and industry, we have seen so far uh, uh, air pollution, water pollution in industry 1.0, 2.0, 3.0. So we have seen uh, air pollution, water pollution, and soil pollution. Now we are seeing this cyber pollution, because it's, we can call it as, we are living in the cyber environment. We are living in the cyber environment. Everyone is using this mostly. They're off of their life, they're spending on this to internet. If the internet not works, they really, they are they are behave mentally. It's a great impact on the social. So all this, uh, there are so many limitations in this industry 4.0. So, and also that, because of this high uses of internet, high automation, because everything is automated. If anything is repeated jobs, if it is repeated job, mostly in companies, especially in the manufacturing jobs, smart manufacturing, most of the cases it is the repeated jobs. So if the repeated cases case, mostly it is replaced by the automation. If everything is automated, so obviously there will be a loss of jobs. Job opportunities will be very, loss of jobs will be in this industry 4.0. So mostly it is in the Japan. Obviously we know that in Japan and Germany, the automation is most them, they are using these countries. They are lost 26 percentage and 24 percentage and united. So in India we have not seen that much, in 9 percentage. So there are this have discussed. So these are the limitation, but there still many are there. Okay, so how we can avoid this? So that industry 5.0 come into this picture. In industry 4.0, everything is, we are talking about automation. Automation is, so there will be no humans are required. There will be, everything should be digitalization. And it didn't discuss about the carbon footprint. It did discuss about the society. It doesn't discuss about the society. In industry 4.5.0, then it has, Japan has introduced this, because so there is a lot of impact on the society, and there will be a no interaction between the humans. And because if it is going like this, so definitely there will be a, so great impact on the society. So that is industry 5.0. uh, 5.0 is coming to this picture. It mostly talk about this human centric. The humans should be involved, humans as well as advanced technology. It should be always be, it should be there. At the humans also it should be interact, so that there will be no loss of jobs and sustainability. So it should be minimize environmental impact. Means you should always think about the alternate sources of energy. You should think that. So always we are depending on the electricity, right? So we should, instead of that electricity, we use any other alternative sources of energy, so that it will be carbon footprint will be minimized. And it should be, and it is also talks about the resilience. So it's talked about this, all these three things: sustainability, human centric, and this data. And so, as you know, that United Nations, the 17 goals are, so by 2030 or something, 2035, every nation, every world, every country, and every factory should satisfy these 17 goals, so that uh, it will minimum impact on the society. There should be no poverty, zero hunger, good health and well-being, quality education, gender equality, clean water, and affordable and clean energy, and decent work and economic growth, industry, innovation, and infrastructure. If you talk about, there are 17 goals. There's every factory, every manufacturing system, they should achieve these 17 goals, right? So out of these 17 goals, the 10 technologies, 10 goals are related to the innovative technologies. Out of the 10 innovative technologies, around 9 or 8 innovative talks works on the electricity only. So can we think that? Can we replace that? Instead of electricity, can we use any other alternative sources of, instead of electrical energy, by to produce electricity, right? We need is lot of resources are used. There will be a lot of pollution, air pollution, water pollution, and more carbon footprint, because to run industry, so obviously most of the carbon emission will come from the industries. Can we think the industry 5.0, it's mostly talk about the sustainability. Can we think, instead of electricity, can we use any other alternative sources of energy? Means instead of that electricity, can we use uh, wind energy or solar energy, so that the you can minimize the carbon emission, right? And it should be, so these 17 goals should achieve, every country should follow this. And if you see the difference, if you see the difference between the industry 4.0 and 5.0, same, we are using same technologies. We are using artificial intelligence and machine learning, IoT, Internet of Things, big data, virtual and augmented realities. We are talking about the collaborative robotics, like collaborative robotics. But in industry 4.0, there is a lot of production is increased due to the automation, but it doesn't talk about this, right? It doesn't talk about um, it should not talk about the job. Human interaction is not there. Humans interaction is not there in industry 5.0, 5.0. So there is a increased role of humans in the process, so that there will be no loss of jobs. And it is a efficient mass production, but the job loss will be there. And it is a more flexible and adaptive, uh, and it's mostly talk about the carbon footprint, as I should read as less as low as if any industry should work on that, it should be as minimum as carbon emissions. So, right. So these are the main difference, the comparison, if you see the industry 4.0 and 5.0. And now, so let us move to the additive manufacturing. So what is it? So, nowadays everyone is talking about the additive manufacturing or 3D printing. For example, if you want to, we are right customizing depending on the customer what we need. According to that, the factory or manufacturing sector should work on it. And obviously customer want me the whatever the design you want. If you know the design software, you can make it, and you can make this your your shoes and your spectacles and your toys and your phone chassis, whatever you want, you can make it by using 3D printing. It's using different technologies. That's we'll see in the what where we can use additive manufacturing or 3D printing. It's not only in the engineering, in any other uh, all other sectors are also talking about this additive 3D printing. You can talking about the medical, and you can talk about the architecture in all engineering application and jewelry application, and even food technology application also you can use this 3D printing, right? And so this is one case I want. One patient, a child patient, he was suffering with heart disease, and this heart was built by this 3D printing, and he has a life because of 3D printing. So what we can talk. That's why it's most of them are talking about, even you can build by 3D with less time. Uh, with less time, you can make the 3D printer house. There's the first 3D printer building in Europe. So what is it? It's what is the difference between the additive manufacturing and the CNC machining? So first, let us CNC machining, what it is. So for example, let me see the difference here. The same product here, this is the product I want this. So this is the first A. This is talking about this is the CNC machining, and this is the additive manufacturing. If you want to make this, what you have to do first, you have to take the raw material according to this. For example, if it is 100 and 100, you should take as 1 or 2 above this size. You should take the raw material. And what is the next step is you have to make a holes. How will you make this drilling? The drilling process, there is a drill bit. There's we should take the high strength material than the workpiece. This is the workpiece. You have to make the drills on this workpiece, and this is the cutting tool, you can see. In this, you have to give some rotational speed, and it will plunge into the workpiece so that you can see the uh, after drilling. So there is a lot of wastage of material. And what in additive manufacturing you should design, and you convert into STL file, and the raw material may be different form. Either it is in the powder, depends on what technology you are using. Either it may be wire form or powder form, liquid form. It's a different form. But whatever in form, the same steps we are using in this 3D printing or additive manufacturing. And how it is working here, it is in the see where you want, there only material will deposit, so that material wastage is very less. So there will be, you can see here, here and here, the material will deposit only, and here and here. So like this, layer by layer it will deposit, and you will get the three-dimensional product. So material wastage is very less, and here material wastage is so much, very high. Wastage is high. So that is the major drawback in the CNC machining, or you can call it as a subtractive machine. Here it is additive manufacturing. We are adding the material. We are adding the material to get a product. Here subtractive manufacturing, while removing the material, you will get the product. That is why it is called as a subtractive manufacturing. Here it is the additive manufacturing. Yes. And according to this AST, American Society of Testing Material, they are defined this. What it is additive manufacturing refers to a process by which digital 3D design data is used to build up a component in layers by depositing a material. So additive manufacturing, first we'll take the 3D design data used to build a component. How will you make the component? By using a 3D design software. There are different softwares. In that software, what the component you want, you will make in the that software, and you have to how it is printing or how it is manufacturing in layer by layer depositing material. And so what it is, there are different names. Some of them are called it as rapid prototyping. Some of them are 3D printing. Some additive manufacturing, additive layer manufacturing, additive digital manufacturing, 3D printing, 3D modeling. So all the names are almost the similar. Okay, because it's a layer based, it's depositing layer by layer. We can call it as a layer based manufacturing, or we are adding the material, you can call it as additive manufacturing, a rapid prototyping, because mostly in initial starting days we are used to make the prototype as it is, and rapidly to make the product, that's it's called as a rapid prototyping. What is the main difference between the additive manufacturing and the CNC machining? So, what materials, what the speed, how is you are using, what is the accuracy, how it is, what is the cost, and what environmentally friendly. This I discussed. And what are the main advantages? The main advantage of 3D printing is you can make any complex geometry. Whatever the geometry is, complex geometry, you can make it. But in conventional manufacturing or subtractive manufacturing, it's a little difficult. And build uh, speed also with you can increase the speed with less time you can get it, flexibility in design, no expensive tooling requirements. As you've seen one example here, if you want cut the material, if you want to make a smooth surface, or you want to make anything to work on that material, you need expensive, very very high expensive tools. But here it's there is no expensive tools are required, whatever it may be the material. You're working on aluminum or you're working on titanium steel, there is whatever the material, there is no other expensive tooling are required in this, and very good dimensional accuracy, wide range of materials. Thus another good point is in 3D printing is the same 3D printing you can work on the it work on polymers, it can work on metals and ceramics and composite and even nanomaterials. But in conventional manufacturing process, if it is work on the plastics, it cannot, you can't work on metals. If it is working on metal, you can't work on plastics and ceramics. So there is only for the specific purpose. But one machine, you can use different materials and you can produce complex geometry. And green manufacturing, clean minimum, because it's a very less fumes will be generated and very less waste, so you can call it as the green manufacturing. And limitations, part size is generally initially it is a part size, but nowadays that is also we overcome by this. And production series, it's mass production little is series up to 25,000 parts per year already possible, but still it's still lot of research are going on to improve the production. Material choice, some materials cannot be processed, and parts made by NET show anisotropy, means properties in the different z axis in the there is a compared to the x and y axis, the property in the z axis little low. Yes. Yes. Any additive manufacturing process or any 3D printing process, these are the 8 steps. We should follow this. 8 steps. But the first step is that CAD, whatever you want to make this product. First, you should design in the software, any CAD software. All right. Then it should be there is a you can converting it to the STL convert mix STL format, you have to convert it, and it should be transferred to the machine, and it should be set up the parameters. Like parameters means you can set up the what is the speed you want, or how much speed you want to make, and what is the sorry what is the thickness you want, and you can what is the temperature you want. Like that you can set up some parameter. It depends on the what machine you are using. Then it should once you set up the parameters, then it will start printing. Then post processing. So what is the post processing? There is some supporting material it is there, so that you should remove. That is called as the post processing, and it should be transferred to the application. So there I am discussing about around 6 to 7 3D printing process. All this 3D printing process will follow this same 8 steps. First you have to design. The first most important step in this process is the first you have to design that whatever you component, whatever the job you want, first you design in the any softwares. So what are the softwares? There are many softwares, still plenty are coming. So there are some easy technology, some easy softwares: Tinkercad, FreeCAD, Blocks, Creo, Fusion 360, SolidWorks, AutoCAD, CATIA, OpenSCAD, Rhino. So any softwares you can design that. And what are the limitations, sir? What are the limitations of this additive manufacturing? Sorry. Yes. What is the classification of additive manufacturing process? How it is classified according to the ASTM? They are classified into 7 types, uh, depending on the what is the raw material and what is the power source. So depending on that, they are divided into 7 classes. For example, if you see the material extrusion, so here the raw material is in the form of the wire, and we are using this thermal energy. And if you are using powder bed fusion process, so in the name itself it is there. Here raw material is in the form of powder, and what are the energy we are using here? The two energies, either it is electron beam, either you are using the laser beam. The two energy beams are using, and depending on that there are different process. If you are using laser beam, so we should talk about this: selective laser sintering, direct metal laser sintering, selective laser melting. If you're talking about if you are using electron beam, then you should go for this electron beam melting. And another process is the VAT photopolymerization process, or SLA process, stereolithography process. And other process, material jetting, binder jetting, and sheet lamination, and the directed deposition process. So let me discuss about these technologies. Let me give introduction about this, and I want to talk about the application also. So this is the first technologies in the 3D printing process. It is called as the VAT photopolymerization process, or it is also called as the stereolithography apparatus. There are different names or different classification: continuous liquid interface, scan spin selective technology, solid ground curing, stereolithography, or stereolithography apparatus, two photon polymerization. But mostly we'll talk about in this VAT photopolymerization or SLA process. And mostly if you have this, mostly the form labs, this is the manufacturing company, they are very good at this in this apparatus SLA process or VAT photopolymerization. So it's this is a VAT is nothing but it's a container. In this container there is will be a liquid resin, and there is a in this platform, means on this platform the printing is taking place. First, the first step in any 3D printing process, the first step is that we should design the component. What the product you want. For example, you want H shape. So the the laser will move according to the H shape. Where the laser is moving, so there is a liquid resin is placed, because this energy either using UV rays or laser energy source. If you want high power, you have to go for laser. You want less energy source, then you can go for the ultraviolet rays. So this energy source will come into contact this liquid resin. Wherever it is contacting, there the liquid resin will convert it to the solid. That process is called as the photopolymerization. That due to the intermolecular, so there will be a, because of that high energy, so the bonding will takes place between the one monomer to the another monomer, so that it will liquid resin will convert it to the solid. So that process is called as the photopolymerization. That is why it is called as the VAT photopolymerization, or it is also called as the stereolithography apparatus process. So once the layer it is move according to your shape, wherever it is shaping, wherever it is moving, that liquid resin will convert it to the solid. One layer is completed. So what is the next step is the platform will or elevator will move one layer downward, and again the new liquid resin will be placed on this solid, and again the process will be repeated. Again the laser will come into contact wherever it is contacting that laser. So that due to that high energy, that liquid resin will convert it to the solid. Again one layer will move downward. Again the, yes, like this process will repeated. You will get the three-dimensional product. As simple as it is, very good it is. And so very good accuracy you will get in this process. Sorry. It is more simple. Yes. And what is the layer thickness? It's possible. Each layer you can go up to 0.076 to 0.5 mm depending on the capacity of your machine. And you need always remember that you, if you want high accuracy, you should go for the less thickness of layer. If you want rough surface, if you are using rough product, then you can go for the high thickness. So where you can go for the high thickness, where you don't want the surface finish, and you want with less time, then you can go for this. If you want very good accuracy, very good strength product, then you can go for the less thickness of the layer. And as I told, what are the starting materials? Here is the liquid resin or liquid monomers. The scanning speed. So scanning speed, you can go for the 500 to 2500 mm per second. So depending on the, in this also depending on the capacity of the machine. So if it is high capacity, the speed is also will be increases. And what materials here, only this SLA process used only for the plastics and polymers. It's not for the metals, only you can go for the plastics. And very good accuracy compared to the fusion deposition, another classification of the 3D printing. You will get very good accuracy and relatively quick process, and maximum weight up to the, you can print up to 200 kgs. Relatively expensive. FDM, the 3D printing, it's cheaper than this, and lengthy post processing time because it needs more supporting structures. Yeah, if any overhangs, it will take a lot of supports, so that we have to remove it. And also that there is a chance of the damage of the actual product. So that is the limited material use of photoresins, and often requires supporting structures and for post curing of the product. And this product is as not the strong, so that is that. So, so this is about the SLA process. The another 3D printing process is the material jetting process. So because of this advanced technology, because of this we are in industry 4.0 and 5.0 is talking about. So there is your no need of present here. So just if your printer is at home, that at office you can see what's happening in that 3D printer because of this IoT and AML technology. Because of that because due to that AML technology, optimize the parameters because of using various big data and AML technology. Optimize the parameters means like what are the optimize the parameters means at what thickness, at what layer thickness you will get very good product, and with less supports where you need the supports, with less supports are required. So all this, by using this technology you will get it. And because of due to the IoT internet connections, you can see it will connect from the system to the your small device. Either you can see in the, you can see in your mobile what's happening in this. If you want to stop the machine, you can stop it. So from with a remote area also you can work this due to this advanced technologies. I don't know why it's see that see the accuracy is here. You can use this small uh, dental applications and very minute parts. If you want to manufacture, it's a very good, and you can use it in the jewelry applications also. The next manufacturing process we are talking about this material jetting. So this there are different names: drop on demand, polyjet, object, multijet. Okay. So let me talk about this process. So what in this process is the same here also. The material is initial material is in the form of the liquid resin, the liquid photopolymer. So in this blue color is the photopolymer, means what is the printing material, and this is the orange color. You can use it for the support material, or for the, or also you can take one more color and you can use two different parts at the same time. You can produce here. So one part one color, another part another color, you can make it by using this. And the other is that you can use with the different material, so that where the less strength you can use the less strength material, where you need the load is acting there you can use the high strength material. So different advantages you can using this multi-jet technology. So multi-jet technology, there is a from this for this blue material is actual printing material is depositing, and here it is the supporting material. For example, here it is overhangs are there, right? Wherever is overhangs, there is a supports are required. Otherwise, it in air it cannot print, right? So for that, it needs some supports. That supports you can print with the dissolvable material, means if you place in the liquid, if you place in the some soluble liquid, if you place that, so this material will dissolve and you will get this product. And the principle is here simple. This is the platform on this printing is taking place, the same steps. We should first you have to design the data, and this material will be jetted. It's called, that's the reason it is called as the material jetting. This material will be jetted on this platform at the same time, and UV rays will be coming, and material is jetted here, and UV rays will be transferred from this device, and it is focused on this. Wherever it's focused, there it is the that liquid resin will be converted to the solid. So the major advantage here, wherever you need, there only material will be jetted. If you see in the SLA process, the entire is the liquid resin, but here it's you need only at this place, so there only the material will be jetted. And again UV rays is focused. Where the UV rays focus, there will be converted to a solid, and again the platform will move downward, again material will be jetted, and UV rays will be focused simultaneously. Wherever the UV rays focus, immediately after jetting, immediately focus the UV light so that it will be converted to a solid. So like that you will get the three-dimensional part. So let me show the some examples here. So you can see the multicolors. There is no other 3D printing or no conventional manufacturing, it's not possible. So that much accuracy and different colors and different plastic materials you can print by this process. That is the beauty of this technology. Very good accuracy, multiple material parts and multiple colors. So I will show this. I'll show this. You can see that so medical industry often use this. So there is no other technology you can talk about this. You are seeing this, right? The outside is one color, inside is different colors. And thing is that all the entire product is manufactured on the same machine, the material jetting process. Like that any can be. So there is no other technology in, so for example, especially in the conventional manufacturing process, if you want to make, so you should make by one method, one machine, or another, it's another machine, and it should be assembled. So but in this technology, and there will be a lot of wastage of material. It's in this 3D printing you can't, the same machine, and all the types of material, all colors will be printed on this. So let me see this. What are the limitations, advantages? Multiple materials, multiple colors you will get and can be printed. And smooth parts, very good accuracy and good mechanical and thermal properties, and high accuracy up to 14 micron meters you can print. And limitations, support materials is always required. So that is a one limitations in, you can see, in 3D printing. And mainly suitable for the non-functional prototypes. If the load acting on the part is more, there you cannot use. And photosensitive, there will be loss of strength over the time. Especially you can't print the large parts, and cost of these technologies high than the other SLA process and the FDM parts. And applications, especially the visual prototypes. So visual prototypes, multiple colors you need, there you can use. And some automatic anatomical medical motors, that in medical device you can use. And casting patterns, end use patterns, special effect pieces, some models, presentations models, and mixed tray painting. So there you can use this material jetting process. So you can see the different colors. So all these parts are manufactured or printed on this the same machine, the material jetting process. The next technology I'm going to talk about, this binder jetting process, is yes, binder jetting process here. So this mostly they are working on Radington, they are working on this binder jetting process. The cost of the equipment is also very high. So in this technology, you can work on plastics, you can work on metals, you can work on ceramics and composites and different materials you can work. So because of the raw material is in the form of the powder. So here is the there will be two platforms. Build platform means here the printing is taking place. Here is the powder supply platform. From this powder will be supplied to this platform. So first step is that initially there will be no powder in this, and here it is the full of powder, and there is a roller. The purpose of the rolling is this leveling roller is to supply the powder as well as the leveling means you it should be flat, it should be smooth, then only you will get the uniform, you will get the accurate product. If there is any mismatch, you will lose the geometry, and you will lose the obviously you will lose the strength of the part also. So the purpose of the roller is to supply the powder as well as the to level this. Okay, initially there will be a powder, whatever it is. You are using plastics, then you have to use powder. Uh, you can use plastic powder. If you are using metals, metal powder. You can use ceramics, you can use ceramic powder. First, there is a powder, and once this roller will move from the left to the right, the powder will be deposited on this building platform. After depositing, the binders, there will be different binders will be used. So just let us focus on this just principle I'm telling in the all this process. So whatever, wherever, if you have any doubt, you can ask me and you can interrupt in between. And after supplying this powder, the binder will be jetted. Where the binder is jetting means the binder, different binders used for the different materials. For example, if you are using for the steel, then it's a different binders. If you are using aluminum, you are using different binders. So binder will be jetted, like it's simply is like glue. Here also we are using simply bonding the particles will be take place. It should not, it's not that has high as, not that much bonding. Just because of that binder, the powder particles are stick together and you will get a solid layer. Once this layer is completed, this platform will move one layer downward, and this will be move one layer upward. One layer it will move downward, one layer upward. Again this roller will move, again the powder will be deposited. Once the powder is deposited on the building platform, again the binder is jetting. See here, where the binder is jetting, there only it is the sticking or bonding taking place, there only solid taking place. And remaining powder, you can, wherever the binder is not jetting, there you can reuse it again. Again, the process will be repeated. Again, platform downward, this platform will one layer upwards, and again roller will move left to the right. Once it's left to the right, powder will be supplied, and again the binder is jetted, so that you will get the three-dimensional part. So like that, you will get the three-dimensional part. But it's not just binding; it's like binder. It's not high. If you want high strength part, if you want, so what you have to go do is, so you have to heat treatment. That is called as the post processing. It comes under the post processing. So depending on what strength you need, and depending on the what material. For example, if you, so all the different materials, you have to use the different sintering temperature. Sintering is nothing but it's a, you have to go for one third of the melting point material. For example, if it is aluminum, the melting point of aluminum is what, 670 degrees centigrade. So you have to go for one third of that sintering temperature, so that, and the soaking time means how much time you are keeping. So depending on the size, depending on the part, depending on the material, you have to go for the soaking time, then you will get the, finally you will get the strength. Oh, sorry. Why it's coming this? The same example is here binder jetting. See here, and what materials it can be used. It can be used for the different materials. The same machine, you can work on metals, you can work on polymers, ceramics. There is no other machine in universe. It's work all the materials. It's work on the same machine. Not only that, different materials you can work on combination of the materials, you can work on combination of whatever the, so that's why a lot of research is going on this binder jetting process. Even I too written two review papers because due to I got less slots in Radington to work on the ceramics, but cost of the equipment is very high. That's. And what are the types of binders you can use? Furan binder, silicate, phenolic, and these are some of the examples of binders given. And the binder jetting, the beauty of this technology, you can use different materials, you can use different colors. The process is generally faster than the other, and the supporting structures are no express support structures are required. It's not always suitable for the structure. If the load acting on the part component is very high, so there you cannot use because of the binder material. But after post process and severe post processing, you can go for that. And you can see the, so all these parts are uh, manufactured by this binder jetting process. The 3D systems, it was this the component was manufactured. And the other thing is that the one point is I missed it, and the technology in this technology, so where the load acting on the component is less. So see here, so if the load acting on the component is, you make it different design, so that what happen, the wastage of material is very will be very less. You can you can save the material, and you can save the cost, and even you can save the time also, because you're not depositing entire material. It will save the time, you can save the cost. So where the load acting is not that much high, there you can use this structure like this. You can place it so that uh, you can save the material, you can save the time, right? So like that, all these parts, it was x1 is the one technology that we used to uh, uh, using this technology excessively in this x1 is the US based companies, US and Germany based. And this 27 traditional components into a reduced into a single piece. So different, if it is, if you want to make by conventional manufacturing process, you have to use 27 machines, you have to make it work. But in this, the all these components, it's manufactured on the same machine. The 27 components on the same machine, it's see how much time it saved, and how much carbon footprint is also, because each machine you have to use a lot of electrical energy if you want to make this, but all the components are makes on this same machine. Especially industry 5.0, it's talking about the sustainability, uh, how you can reduce the carbon footprint. So if you are using this technology at the same time, if when will you know human involvement, it should be also no human, uh, uh, and robots combinedly should work in this industry 5.0, so that it will you can use the alternative sources of energy. So where you can use other technologies so that it will reduce the carbon emission by using this technology. A and ML is there, and big data analytics or cyber security is there. So with all this technology, so because of it will optimize the process. It will optimize the process. It's like, so where the supporting structures are not there, and it will where you need less supports are required, where the load acting is more, and what component you can use. So all by using this AML techniques you can optimize the process parameters, right? The C here, the same component. For example, here in this weight is 7.8, and here is reduced to 2.5, and then still it is reduced to 1.40. See how it is 7.0 and here it is 1.40. So this is this these parts you cannot manufacture on the conventional manufacturing process. It is not at all possible. See here, to save material, especially for the high strength, high cost material. For example, you're working on super alloys, or you're working on titanium, or you're working on nanomaterials or composite materials. The cost of this material is very high. Okay. At the same time, you should not compromise the uh, selection of material. So you have to use that high strength material, as well as the design we are not compromised. But here it is where the load acting is less, there you're remove the material in terms of they are making some patterns, some square pattern, some hexagonal pattern. If you make it, so you can reduce the weight of the component. The same component, it is reduced to 2.8, optimized, and still optimized, then it comes to the 1.4. So that's the beauty of this 3D printing process. Whatever it is the complexity of the job, you can easily printing on this 3D printing process. And this is one of the another multi-part, it's printed on this binder jetting process. Then the other 3D printing process I'm going to talking about the fusion deposition modeling. Most of them knows about, because nowadays everyone using this because of the less cost. Due to the less cost, even it's if you go for, if you want to buy Amazon, you can buy it for the 14,000. You can buy it at around 14,500. Uh, it's coming here. The cost is around, it start with 15,000. And what are, you can, there are different names for them. Mostly we will call it as FDM, or some of them will call it as the fusion filament fabrication, fusion deposition modeling. So, so this is the uh, this is a schematic picture of this fusion deposition modeling process. So there will be a liquefier. So in this, the heating will be taking place. This is the heating elements, and this is the initial material. How the material is in the form of the wire. The and FDM is mostly we go use for the PLA and ABS. These are the two materials we will use. There are other materials, but most of the time we will use PLA or ABS. PLA is a biodegradable material. That's why most of them are for prototypes will use PLA material. If you want a high strength, little high strength you require, then you can go for the ABS material. And the material will come into this driving wheels, and here heating takes place. That liquefied material will depositing on the this platform. Some cases this platform will move, some cases this nozzle will move. So most of the cases in the printers, nozzle will move. This nozzle will deposit this liquefied material. The ones because due to this heating elements, that wire will be melted and it will be deposited. So and due to that surrounding atmosphere, it will be converted to a solid. And once it's completed, another layer means the base plate move downwards and the nozzle will deposit the material on the printed part. Again will move downwards, again they will be printed. So like that. So nowadays we are seeing the dual nozzle means where the supporting material is you need the less strength material means why the supporting material is the, the uh, with another material means to easily to remove easily, right? Otherwise there is a chance of the damage of the actual part. This, for example, this all this green material you should remove it to get a final part. And if the all the both the parts are printed on the same material, you cannot distinguish what is the actual part, what is the supporting material. So that is the advantage in dual nozzle. And as I already discussed, what are the materials? Mostly we are using PETH, ABS, and PLA, polylactic acid, and ABS. Mostly we will use these materials. So this point was also I discussed this. If you are using similar material, you are using the secondary material also. So if you have secondary material with less strength material, so that easily you can replace. Yeah, easily you can remove it. Just if you're putting in that some high high soluble liquid, then easily it will be dissolved. But if they are printing the same material, it's a little difficult. You should be very careful. You should need more time to remove that. Yes. The advantage are is cost is less, very less, because that's the reason the most of the universities, most of them are even at houses. We are seeing this FDM machine and portable. You can carry anywhere, and compact design. The design of this very and limitation is the warping is logic logging, longer printing time. So while starting, once I started this 3D printing around 2015 or something. So there you are, I've seen so many problems, logic logging and bed calibration, layer adhesion, layer will stick to the bed. But because of these technologies, these sensors, this IoT. So uh, these are all problems are overcome by this now. Because noisy clogging now we are not seeing because due to the sensors, if the filament is not good, so you will get the message. And the layer adhesion problem and bed calibration. Nowadays, all the printers are coming automatic bed calibration. You no need to calibrate. It's a big headache for the starting 3D printers. You should always print to print. You should calibrate the bed. It takes a lot of time to do this, but all this come by this to these advanced technologies. And it's used in almost all the applications where it is music equipments, biomedical applications, some of the automobile parts, some of the aerospace parts, and all household applications, sports equipments, music equipments. So in all these cases you can use this process. And even this FDM parts used in the, you can nowadays we are seeing the Philips. They started this Philips company. They are started this even metals. The same concept instead of plasticware they are using this. They have succeeded this. Then we give the very good results. So instead of plastic filament, you can use the metal filament so that you will get the part. And now other companies, other manufacturing sectors also they are coming to this like metal FDM process. And also this FDM they are using in biomedical application enormously, especially the drug delivery applications. If you want, so uh, mostly, so what we are using here, we are taking the medicine the more than the sufficient. For example, you take any medicine, that's you're taking the more than that. But in this, by using the FDM process, because if you after all this testing, you will take this much medication, this much is required you for this. So that will, because due to this FDM, so that much is possible by using this technology FDM process. They are using. There is a lot of researches going on this, and there is a micro tissues biomedical application they are using. But the cost of the equipment is high because even raw material is cost is also very high. They are using this process. The small videos, because I'm sharing this PDF. I can't this share in this video. Okay, next. Uh, so let me discuss it powder bed fusion. Then I'll conclude this. The powder bed fusion process, another most of the especially metal 3D printing, they are using this technology, especially EOS. This is very good in this, especially SLM, DMLS process. So let me talk about the SLS process, selective laser sintering. So here it is the SLS selective laser sintering. It is used for the only for the plastics. So you not using metals. The same principle, selective laser melting, selective laser sintering, direct metal laser sintering. So in all these cases, we are using the energy source laser. If you are using the energy source electron beam, then you can call it as the electron beam melting. And here it is the laser source. And you can use the multi-jet. So we'll see one by one. So let me discuss about this selective laser sintering. So we'll use CO2 laser. That is enough for this. No need to for the high energy lasers. So here it is for the plastic powders. The same concept is as I discussed in the binder jetting process. So initially the powder, this is the powder supply platform you can say, and this is the building platform. Once the roller is moved, the roller blades, somewhere, some other cases you can use the blade. This roller will move from left to right. This powder will be deposited on this platform. Once it is deposited, the CO2 laser will be focused according to your file. So here is your file is plus symbol. So the laser will move according to that file. So wherever it is moved, so there, because due to the high energy that bonding taking place between the, because of that high energy laser, the particle to particle bonding takes place and it will become a solid. Once the layer is completed, this platform will move downward. So it can be moved up and down. So once it's moved downwards, again this roller will move from left to right and powder will be deposited, and again the laser will be focused. Wherever it is focused, there will be converted into a solid. So like that process will be repeated, you will get the three-dimensional art in this SLS process. This process is only for the plastics. You can use mostly for the plastics. The different polyamide like nylon, high strength polymers you can use, and very fast 3D printing. You can use very complex geometry, very good dimensional accuracy, and compared to the all other plastic 3D printing process, either SLA process or binder jetting process or FDM process, it's give very good dimensional accuracy compared to the all other process. and it will give the very good mechanical properties. You can use the high strength polymers because obviously when you are using the powder there is a chance of the brittle, and post processing procedures are difficult, and only industries you can use. You can't buy this because the cost of the equipment is very high. It is uh, so that's the limitations and applications you are using because of the high strength, high dimensional accuracy. You can use it for the uh, aerodynamic applications, automobile applications, and sports, where the cost is not the matter. There you can go for this process. Next, you can go for the selective laser melting and direct metal laser sintering. So here is the same concept is here, uh, but the difference is the between the melting and lasering is here. The melting is nothing but it's converting to the solid to the liquid state, and sintering is nothing but just one third of the melting point below the one third of the melting point. The same concept is here. This is a schematic picture of the SLM process or DMLS process. SLM is nothing but selective laser melting, and the other is the direct metal laser sintering. So there will be two platforms. Here is the powder delivery platform, and here is the part printing platform. First, initially in this one, there will be a full of supply of powder, and here in this there will be no powder. So here is a recoater blade, or it is a recoater cylinder, will be moved from the left to the right. Once it is moving, the purpose of the recoater, as I had discussed, it's supply the powder as well as the leveling. Once it is moving left to the right, the powder will be supplied, and the laser will scan. High energy will use the high energy laser so that the laser will melt the powder particles, and because due to the high melting, and after that the solidification takes place. So once the layer is completed and again one layer deposited, again the laser will be focused. So like that process will be repeated, you will get the three-dimensional part. The principle is same you as you are using. In binder jetting process, you are using binders. Here we are using the laser energy source. And initially, because you can use for the different materials. By using this AML, you can optimize the parameters, and you can uh, uh, optimize the parameters here. Mainly optimize the parameters at what range it will, what speed you will get very good after uh, repeated number of components, at what speed it will give the good accuracy, and what layer thickness it will give the good part, and where you can use the less supports are required. So that is possible by using these technologies. So here you can see that how it is melting is taking place, because once the laser beam is focused, there it is the melting of this powder particles are taking place, and it will be solidified, and you will get the solid part. See here, this is the there you are focusing, the laser is focused so that you is seeing the solid. The remaining is not focused, there you can see the powder particles. So what materials you can use? You can use all types of materials. You can use, see, the aluminum alloys, stainless steels, titanium alloys, cobalt alloys, and nickel super alloys, and even combination of the materials also possible. Those are working in research. You can there is a chance you can different composites you can work. So the advantages are, so see here, it can be combination of the materials aluminum and nylon can be successfully printed on this, and variety of materials, the it comes to the low melting point to the high melting point materials you can make on this machine, and the wastage will be less, means wherever the laser is not depositing, right, there the powder it's not melting, powder is not sintered, again that powder you can reuse it, recycle, you can reuse it. The limitations are the price is high, but still overcoming by this using this advanced technologies and porous part, because of this powder particles, because raw material is in the form of the powder, you cannot eliminate the porosity. 100% porosity, elimination of porosity, it's not possible, but there will be slight porosity will be there. Small build volume parts, small build volumes. Build volume is the what actual printing is taking, build volume is less in the DMLS process. Application, so where the medical, dental, aerospace, so in all these cases we are using this. So this is the different metal components are made by this uh, SLM or DMLS process. And this is the surgical 316L stainless steel surgical guide made by the laser beam melting, and this is the one component is made. And electron beam. So once I will also discuss, if I have time, I'll discuss another time. Electron beam melting. What is this electron beam melting? The same technology is here, electron beam, and here the electron beam will be focused from this here, and this is the build platform, and this is the powder supply platform. The electron beams, obviously you also knows that electron beam is having very high energy than the laser beam. Due to that, the production process is very fast compared to the either SLM or DMLS process. This is called as the electron beam melting. As we are using the electron beam source, that's the reason it's called as the electron beam melting. So here also, so always remember that selective laser sintering, selective laser melting, direct metal laser sintering, electron beam melting. So all these comes under the powder bed fusion process. So powder will be supplied here. Initial material is in the form of powder, and powder will be supplied in this platform, and electron beam will be focused, and wherever it is focused, there it will be converted to the solid. Once the layer is completed, again one layer move downwards, again the electron beam will be focused. So like that you will get the three-dimensional part. So the limitations of this electron beam melting, we can't use for the, you can use for the which is electrically conductive. If it is not electrical conductive, you cannot go for this technology. If it is, you can't. But laser beam, it can be possible for the all the materials. At the same time, if it is, let me show that. High quality materials, more powerful multiple electron beams, faster printing, because it's a more powerful, high energy source. Because of that, printing speed is very fast. High quality metal parts, high density. You will get the high density parts. Advantage, material wastage will be less. Accuracy surface finish is good compared to the uh, and residual stresses are much lower than the SLM process, because at a time you can deposit high thickness layers. And the limitations are, it should be must be conductive. If it is not conductive, you can remove. And the always point to remember that So thick layers it's deposit. Where the thick layers are depositing, so there the surface finish you will get the rough surface finish. You will, if you want, always remember that if the thickness layer is small, if the layer thickness is small, there you will get the smooth surface. If the layer thickness is high, there you will get the rough surface finish. So obvious of everyone knows this. Yes. And material, so high strength, high melting point materials you can easily produce in this process, electron beam melting. And it's only commercial aluminum solution to manufacturing titanium aluminum. That's very difficult because titanium is a high melting point material and aluminum is low melting point. Okay, so it's a combination of materials because the raw material is in the form of powder, so you can different wherever it's a feasible, and you can work on. Especially the GE is mostly working on this electron beam because of the cost and the production process that you can use, especially mass production. You can go for this. And Titan 50% lighter than the other metal alloys typically used in the aerospace industry and orthopedic implants, especially the titanium, all the implants your by using this EBM technology. See the components, all the hip joints. So all the hip joints, it's easily you can, because it's it's all the, for all the patients you can place the same size. So depends on the customer, depends on the patient, you should design, and you should, or if you want to go for conventional subtractive, it will take a lot of time. But in 3D printing, once you design it, you can make any component or any material. I think I have time. Hello? Yes. As just one point, I can cover this directed energy deposition materials. So let me discuss and I'll conclude this. Directed energy deposition 3D printing process. What's that? You can call it as a DED process. The simple difference between the powder bed fusion process and the DED process is that, so let me show the diagram is here. Here is the center energy beam is focusing. At the side, the powders are depositing. Here the, in powder bed fusion, the powder is stationary and energy beam is moving. In this process, we are moving the material as well as the energy. So wherever the, according to your file, for example, you need, for example, support S shape. So the powder will be moved according to the deposited, this beam will be moved according to the S shape. So the powder will be according to shape it will move. At the same time, the laser also will move on the S. Wherever it is a laser is focused, there the, due to the high energy, this powder will be converted to a solid. Again, the process will be repeated. You will get the three-dimensional part. So you can use all different materials, combination of materials you can use, and it's a 5 times. It's very fast because uh, 10 times faster. You can 5 times little expensive than the powder bed fusion process. So due to this limitation of time, I'm not this covering. So it start with you can, if everyone knows about this 3D printing, it's okay. If you don't know, start the 3D printing. So very easy, you can start up and you can make small components and you can. So nowadays people are working on this, even food production also you can make cake by using this FDM 3D printing. You mm, and they are using drug delivery applications. So those are working in bio, especially if you are in research, they you can. And if you want, especially for the industry and education institutes, this is little cost is high, but speed of the equipment is very high, fast, very fast in this bamboo printer. So thank you for giving this opportunity for KIIT. So let us sacrifice today so that our child can have a better tomorrow. So we are living in cyber pollution. So half of the people are, is according to the recent survey, Ford survey. So 67% of the people are using this internet, and in that almost 70% half of the time the spending on this uh, internet only. So means unnecessary platforms we are working. So even recently Australia also, if you're the child less than 15 years, if anyone is using um, as less than 15 years, so it should be, there will be a case against for their parents. I don't know how it is true, how it is recently. I've seen that post. But let us sacrifice our today so that our children can have a better tomorrow. So thank you. If you have any query, so I'm ready to answer this.
Thank you, Professor Venu Kumar. Now the panel is open for a couple of questions from participants. Any questions? Yeah.
Sir, good
Yes.
evening, sir.
Sir, good evening, sir.
Sir, actually, this 3D printing, you see, nowadays 3D printing is available or advancement 3D printing is available, but still it is not possible to whatever materials you can use to fabricate any type of material, any type of production. So it is not possible, na?
No, sir, it's now it's possible. Means what type of material you are using that.
Suppose in fabrication, suppose we want to fabricate any composite material,
Mm.
like your stair casting is there, powder metallurgy is there. These are the different processes are there. Suppose let us we can produce, we want to use aluminum alloy and any filler material to fabricate the 3D printing. Is it practically possible?
Yes, sir, it's possible. Most of them are working now. Recently started FDM and this SLM process. You can make composites, but little starting the cost is very high. That, but if you are making the number of components on the, if you increase the productivity, the number of components are more, so the cost will be reduced.
So, sir, where that machine is available, suppose this is a high-end machine, so it is not practical, everywhere it is not available. So, can you give the details where that material, the machine is 3D printing machines, higher version is available so that,
Sir, if you are working on metal 3D printing, especially composites, if a metal FDM, the Philips company, they are working, they are ready to work all the research scholars also. And most
Philips
of the
company?
IITs and most of the even private startups, they are started this. Um, and if you want powder bed fusion process, if you want powder bed fusion process, and EOS, and there are other companies, they'll ready to help. And in all the education means NITs and IITs and some of the good private universities, they have these facilities. Oh, if you, I'll give the ready to help this, especially what material you're working, then I'll ready to help where you can go this.
Okay. Thank you, sir. Thank you, sir.
So, any more questions?
Hello, good evening, sir.
Yes,
I'm Chandrasekhar from Hyderabad.
yes.
Sir, could you please highlight the latest research areas in the field of additive manufacturing? And also, do we have any professional body members and the research centers to undergo research?
The first question is what, sir? The first question is
The latest areas.
mainly research area is working on the different alloys and different composites, and especially bioprinting. The mostly they are working now. Bioprinting and this construction is also still a lot of research is going on this, even in construction field also, and even food 3D printing also. It's still it's going on this. You can work on that.
No, as I'm
And
into
research
mechanical engineering
centers.
background,
uh,
as I'm into mechanical engineering background, could you please help me out in this regard?
Mechanical background, so you can work on composite materials, uh, especially the latest technology is the metal FDM is the good technology you can work. And if you go for the DED process or DMLS process, you can go for the very high advanced alloys, different combination of materials and composites. And even you can work on, so for example, if you work on especially this powder bed fusion process, the you can deposit some nanomaterials also, so there you can work. And even binder jetting process also you can work on this ceramics. Very less work in, especially in India, less work I am seeing in it, the ceramic research you can see that also. Binder jetting, so you can contact the X1 and Radington, they are companies they are working on that. Just looking.
Professional bodies for additive manufacturing and research centers.
Recently Hyderabad, they have professional bodies. I don't have that much idea. That's
Okay. Any research centers in
in all
Hyderabad
the
or in Telangana? Some.
in uh, Hyderabad, you can see the IIT Hyderabad and Osmania University. They have powder bed fusion process, and the metal FDM Philips. It's in Bangalore and around Chennai. In Chennai, there are many companies have there's a list, many of them working. So if you want, I'll give message.
Sure, sir. Thank you. And for any further queries, I'll be mailing you. Please kindly help me in
No,
this thing.
thank you.
Thank you very much.
Any more questions? Well, I think no more questions from the participants. And of course, they will catch you, sir, if they need any help. And thank you so much, sir, for making out time for us. And I hope all the participants will definitely get benefit out of it in their research field. So thank you all the participants for your active participation in this session, and wish you all a very great evening ahead. Good night, and see you tomorrow again.
No,
Thank you.
thank you, Kate and ma'am, for giving this opportunity. Thank you all.
Thank
Thank
you.
you.